Everybody's inside. The room is fully packed. Yesterday we dropped a few tickets from the waiting list, and 2 people got a ticket. So there's always hope. Always believe in your dreams, because the way it works is we put all the chairs together, and we realize, oh, actually we can fit 2 more people inside. And all right, so again, thanks to our sponsors. I saw on Twitter that James from IBM was in our direction. He still hasn't arrived, but thanks to IBM and thanks to Lodom again. And let's go to the next speakers. So 9 more to go. And the next one, Manu was already here last year, for those who remember. I tend to swap almost every speaker every years, but I always keep at least 1 or 2 speakers. We really liked your talk last year. So here's your mission. Make an even better talk this year.
Okay, no pressure.
All right, ladies and gentlemen, Manu, Rink.
Good. So first of all, to make a good gig and that I can come next year again, I thought, let's drop all the live demos, because then nothing can go wrong, right? And
Something can go wrong.
yeah, I'm umschalten. And today I will kind of cover the boring stuff first for you, because then all the awesome stuff is coming afterwards at the conference. And I thought, why not give you an insight, or let's deal with types, just types in general and types in Swift, because most of us are using Swift on a daily basis. So yeah, please, because otherwise everybody has to look there. Yeah, here we go. And I thought it's quite interesting to really get an idea of how a type system works, but we won't go down very deep. We won't go down to the compiler tree stuff where everything is interpreted. We really stay on the implementation plane, just for you to get a better idea of how Swift really works for you, and where the magic from type inference and so on really comes from. So that's the idea. Good. Then just to get out some confusions, everybody knows Swift. We are talking about the programming language Swift here. And we are now actually, so I can drop this. We can actually use version 4 right now. So we've come a long way. I don't know how many of you are using Swift since the beginning. It's not that long ago, but a few of you. And the pain got much more less, I guess. Much more less. Yeah. So by now we have things like, I wrote it with a little star on it, we have downwards compatibility. So our subversion of Swift is not tied to an Xcode version anymore. Yes, it is, but we have the possibility now to use 4 and have the possibility to use 3.2. And before we had 3 and 2.3, I guess. So we have kind of a compatibility here. And we're going forward with having encoding, decoding made comfortable, strings or collections, again, kind of for us Mac and iOS developers. We have one-side ranges. I don't know if you used them anymore before. Dictionaries got more functional. So the language is really evolving with quite a fast pace, I would say. And making it open source and getting the whole community in for really getting feedback from what do programmers and developers need from the language is a real improvement for the whole thing. So I think that's not bad, actually, but we're not there yet. As you know, we don't have ABI fixed yet. A lot of things for example, await statements like C# and other languages have it. Swift doesn't have yet. So there is a way to go, but where we are compared to where we have been 3 years before is quite a good way. Good, so that's kind of my idea from Swift is not bad, but what do developers out there say? So the IEEE Spectrum always makes surveys couple of times a year, and then they pack together the whole popularity and how many readers use which language, how they favor one language in comparison to another one. And Swift is here on the overall spectrum of developers out there, already in top 10. So that's quite an accomplishment for such a young language. And when we go over and have a look at what's trending, Swift is even at place 5. So that's quite something. And when we throw out all developers who are not mobile developers, so really have a focus on our community, on our folks, we are on place 6 and even before Objective-C right now. So it already shifted over. So people are leaving Objective-C in favor to Swift. I know not everybody, because there are some dinosaurs out there who say, I don't leave my home base. Yeah, I stay with Objective-C. I even make it Swifty, yeah, to stay with Objective-C. But they're Swift now. So it's really, it's going forward. Good. And yeah, what about types now? We want to talk about types. So when I first came around with Swift, I thought, cool, kind of nice, because I was coming from the Java side. That's what I did years and years ago. And then I had to deal with Objective-C, and then Objective-C told me, I have an array or dictionaries for you, even an array, and you can throw in there whatever you like. And I thought, what? This is not possible. And then Swift comes around and says, hey, good news, you're now back to the Java times. So you're going back in terms of being an Objective-C developer to being very, very strictly, so to get stricter rules now. And when you think back to the first few hours you spent with Swift and the Swift compiler, you already had the feeling to satisfy the compiler and don't get your things done. So it's really just making types right, being restricted to something. So that was my kind of feeling. And that's why I started to really dive into and understand why the Swift type system is in place like it is. And it's actually a good thing. And that should be the key emotion with which we are going out of this talk. Good. So it's all about types. What I'm doing is when I start with something, I make a picture of it, because otherwise I can't grasp it. I can't really visualize it. So this is the Swift type system, kind of covered everything which is in there, which is necessarily in this implementation layer. And we will cover all of it in the next 30 to 40 minutes. And I swear it's not difficult or illogically. It's nicely to comprehend. And you'll be able to understand everything of it afterwards. So we will start with the left, right part, anyway, with the part over there, because I have two statements I wish to place in your heads. So in Swift, there is no root. And in Swift, there shall not be nil. With the star you saw before, with stars always is, there is something else, because there is basically not nil, but in some cases you can do it. But just keep in mind there is no nil, and we don't have any roots. And so actually Swift doesn't have a root type, a root node. There is nothing like this. Because in other languages, we know there is NS object, there is object, for example. Everything is kind of inherited from it, but Swift doesn't have something like this. And it's really kind of interesting to see how the types can be constructed in a very nice way without having a root like this in place. So that's really nice. To get an idea of it, I thought, let's take the type integer. Everybody of us knows integer, uses integers. It's basically just a number, so not a big deal about it. We're using it in various ways. So in Java, the inheritance is quite low, I would say. We just have object at the very top, because object is on top of everything. Then there is a number, because Java has a lot of numbers. So float, for example, is a number 2, double is a number 2, and we have the integer. So that's okay. And it conforms to interfaces, as they called in Java. Not that much. So how does this look in Objective-C? we have the NS object at the root, and it conforms to some more protocols compared to Java. Good. And in Swift, we just have int. There is no inheritance there, but there's a lot of conforming to protocols. And as I saw this the first time, I thought, whoa, this looks kind of chaos. Int is somewhere constructed out of this chaos. And there's a quite nice swiftdoc.org, and it draws you a graph of your type. And this is int. So this is int with the latest, the pre-version of Swift from 3.1, but I think it didn't change anything with 4.0. So as you can see here, a lot of things are constructing our int, but there is no inheritance per se. And that's a good word, because a lot of protocols are constructing integer. So the int and float and string and all those basic types in Swift are structures. They are structs, and they're not classes. So that's kind of huge. So I thought, okay, is integer very special in the Swift world? No, it isn't, because when you have a look at float, it kind of looks the same. So it's a very broad and kind of high implementation and conforming protocol structure. And in comparison to a dictionary, which I thought, okay, a dictionary is more powerful than a simple number type, the the conforming structure isn't that great, basically. So it's kind of flat. So what are the types in general? Because we have no root, we have the possibility to couple functionality quite loosely to really extract our concerns in certain parts and then reuse it to a lot of different structs or to a lot of different types. And that's what Swift does. So you don't pack everything together in one class and say, this is my functionality called int, it's a number. You just place the functionality in a lot of different places and then let it really conform to one piece. So that's the idea. And the interesting thing is, there are really just two types of types. So if it's an int, a float, a string, or whatever, you can break them down to two types. And those types are called name types and compound types. And guess what? Compound types are made of name types. So you are using exactly this part of the whole picture in your everyday work, because you know and use all the basic types. You are using collections, which are just a super form of your basic types. You're using functions. You're using closures. All of those things are basically can be broken down to those two types. And I would start with the name types, because those are pretty easy to comprehend. Name types are all types which have per se names. So those are classes, structures, enums, and protocols. So everything which you can give a name or the framework already gives a name for, those are name types. So that's kind of easy. And everything, as I said before, which is a number, a string, dictionary, arrays, all those things are structures, are struct in string. In Swift, I'm sorry. So when we have a look at the integer struct, it looks like this. And please see the 3 dots here. I think this list is going down 4 or 5 times. So it's really a big collection of functionality, which the structure int holds for you. And it's not that much, as you see here, just 3 protocols. This structure definition of integer itself holds, because everything else, which we saw from the, I think, 11 or 12 protocols int is conforming to, is placed with extensions in completely different places all over the language to integer. So that's how this whole struct really comes to place. And you can, so what you're doing too with your classes or your structures, you can extend them from somewhere with some functionality. You can add to those structures your own functionality if you want to with an extension, and nothing else is done by the language itself. So it's really just a small part what integer itself is, and the language itself puts additional functionality to those types. So that's how the types are constructed in this way. So the basic types. Good. So all of this comes together here in the structure of int. Sorry. Good. Okay, so next up, the compound types. So they are kind of making use of the name types. And as you see immediately, you know them because compound types are tuples and functions. So those are the two forms of it. And you are using tuples, maybe not always in a very explicit way, but with an implicit way, you're using them a lot. And you're using functions or function types in every function and every closure you're writing. But we are seeing this in an example right away. So tuple types. I'm sure a lot of you guys have used this notation before, I guess. So just don't define a structure, don't define a class, just put values in parentheses, give them parameter names, use them. And this here is basically a type of int, but you didn't give it a name. It doesn't have a name. So you just assign it to this variable grade tuple, and grade tuple is now from the type int. It doesn't have a name like array, like dictionary. It's just this tuple, actually. And you can now assign another tuple to it. You can leave out the parameter names and just assign the values to it. You can access it with the index or with the name itself. And what do you think happens with the two examples down here? So basically, we are assigning a tuple with two ints again, but we are exchanging the parameter names. Or down here, we are defining the tuple with the exact parameter names, but with different values. And as you might guess, this fails. Because what did you do? Or what did Swift do for you? You attached or assigned this int tuple to the variable. So Swift inferenced the type for you, which is int. And as soon as you want to attach another tuple or with another with another types in there to the variable, it's like trying to assign a string to an int. So it just doesn't work. So keep in mind, as soon as you are using unnamed types, you are really typing, or Swift is typing with the type inference system this very value for you. So in any case, you might be wondering why this breaks. It's really because of the variable gets the type. It's unnamed, but it's a tuple. So that's it. Good. This is basically the use case you would use tuples for, just to throw back a couple of values from a function. And this is done here, where a function is defined, where nothing comes in, but you are returning a tuple of UI color, and give it the parameter names foreground and background color. So that's it. And you're doing something here and then returning the two values. And it's really just, again, you are constructing a tuple here with the two types in there. They conform to the exact type which you defined here, and that's why this works. And then you can store this tuple here at a variable because you're returning it from the function, and addressing the values with the parameters or with the index. You can exchange this background here with just a 1. That's possible too. So this is kind of what you would use this idea of a tuple for. Good. And what you can do too, a tuple type is basically an unnamed type, but what are we used to? We are used to names. So you can give it names. And you can define this thing here, like we saw before. This is just an unnamed one. And then afterwards you see, okay, I really want to address this thing with a name and not just guessing what type this variable is. So I define a type alias with this exact type assigning to the name point. And then I can just create a new tuple with name point and the values in there. So this kind of looks like a constructor, but it's for you made possible with just this tuple notation. And then you can, as soon as you did this, attach just different ways of constructing those tuples to different values actually. But keep in mind, you can give those tuples whatever name you want to. And I really just tried this out today because it crossed my mind. Swift tells me when I'm kind of defining a type alias which is already there in the system. No, it doesn't. So I defined my CG point, which is 2 strings, because to make the confusion complete, so it's not 2 CG floats, it's just 2 strings because it's my CG point. And then I'm just saying, hey, I want to have a new CG point with this is dangerous in there. And the compiler says, hey, go with it, have fun. So really keep in mind to name your tuples or your type aliases really the way it doesn't get in any way with the language itself. Basically, it doesn't get in the way with the language, but it will get in your way with debugging this thing when you are looking for, hey, did anybody define CG point somewhere else? So that wouldn't be your first thought, I guess. Good. What's that? It's void, as you could guess. And how is this empty parenthesis made possible from the language for you to use it as void? Because Swift doesn't anything else than making a type alias from an empty tuple. Because nobody said that always 2 values have to be in a tuple. It just says you can put values in there. And when nothing is in there, it's just void. And what's that? As I said before, you can put any number of values into a tuple, and Swift says if you just put 1 value in there, you can drop the parentheses because don't write that much. And this is exactly how your data types which you're using, the basic types, are coming into place. Those are from the language itself offered to you as tuples with just 1 value in there. And then Swift says drop parentheses, use it as they are, and then you can exactly write int equals 23 instead of putting parentheses in there. What's really happening under the hood for you? So Swift is doing a little syntactic sugar for you here. Good. So much for tuples. Now we know that we can put in parentheses a various number of different named types together, give it names with type aliases if we want to. And those tuples are needed for functions because you know how you write functions. You have the parentheses, you define values for input, and you define values for output. And this is nothing else. This is a tuple, this is a tuple, this one, this here. Those are all basically tuples. And as soon as they are put together with those little arrow, then they become what we always, so we developers say, this is the function signature. But what it really is it's the function type. So your function is a type 2. And think about it, you can assign a method or a function to a variable, and the variable gets the type of the function because your variable, your value always needs a type. And that's why functions are types 2, but just with attached closures where you put your code block in. So this is actually what Swift offers you. Again, little bit of syntactic sugar. Basically, when you don't want to return something from a function, you would have to write that you don't do this. But Swift says, hey, when nothing is returned, I notice it, so just drop it. You don't have to write anything. And when you want to return, as we saw before with the UI color example, different values from a function, you can put it in a tuple, or what basically, because we are clean coders, right, want to do is put those together and give it a name, and then make a struct of it, because we want to attach further functionality basically to those two values. So we define a struct. So what is a struct? A name type. Put those here in. So we can drop this tuple because we defined our struct, use the struct as a return value because we are just putting one value in. We can drop the parentheses and we end up with this notation we are used to. We can just return one name type. And yeah, you can play this game as long as you want to. You can use now this name type struct, which you already created here, again in a tuple. So yeah, type system. Good. And I had to put this in here because I don't know how of you guys did ever nest a function in a function for a good reason. Yeah, I thought so. So you can do this. I don't know if you should do this or if your use case makes you do it, but then the notation gets super funky because you have to define the in tuple, the inner in, and then the real out. And as long as you nest, this inner in gets even longer. So you can do it. This is how it looks, but I don't know if you should. But in any case, Swift gives you the tools to construct cases like this. Good. So as already mentioned, we can use function or function return values on variables. And this is what we do on a basically daily basis. We can define different functions. This function doesn't have any return value, and just gets an in, and the next one doesn't get anything in and returns an integer. So nice. As soon, it's basically the same example like the one with the tuple before. As soon as you assign this function to the variable f gets the type of the function. So it's bool void, bool in, void out. So that's it. As soon as you want to try to assign this other function the steps to home to f, it fails because you are trying to assign a void integer type to a bool void type. Again, like assigning a string to an integer, fails. So everything comes basically down to this: keep in mind what type your values currently have, because they might be inferred with things like this. And just for a mentioning, you can use the variadic parameters too in Swift. And this is just make 3 dots. Then you can add as many values from the same type. This is important. You can't add int and strings in here, so really just this one type. As much as you like, and Swift then offers you an array basically for exactly this value. You don't have to define the array in the function type, so really just use it afterwards within the function block. Good. So we talked about functions. The natural logic tells us to talk about closures. So closures basically use function types for their signature, because even a closure needs to know what comes in, what goes out. And this example here should show you how we can shorten code, like this little piece here, very dramatically with the usage of closures, with the usage of type inference, and a little bit of syntactic sugar, which is offered to us. So this example is very basic. We have a string array. We define a function which just compares 2 strings and returns which one is greater. And this function is then offered to the sorted function of the array with the by parameter. So that's kind of very explanatory code writing. It's very verbose. We read it, we know what it does. But we can do it a lot shorter, actually. And the first thing would be get rid of this external function. Just use the following closure and put your comparison code, which the by parameter here needs, just really as nested within the function call. And that's it. We have to write our function type in here, so the signature kind of, that two strings are coming in, a bool is coming out, and then we are returning the two values in here. So that's exactly doing the same like this up here. We can do it shorter, right? Yes, because Swift knows, because the array defined the sorted function, Swift knows how the parameter looked like. And that's why you can drop the types here. You don't have to say parameter S1 is a string, because Swift already knows this, because the string structure itself defined this on the sorting function. And that's why we can write it quite shortly. But what happened with the return? As soon as you just have one line of code in your block, this is automatically returned. So you don't have to write a return here, skip it. And that's why you have a very nice short definition of what should happen when your array should be sorted. So that's it. But it can be shorter, right? Yes, because Swift offers you shorthand parameters. And that's always the case when you have, like in this case, two parameters in, one out. So you can say the first parameter is $0, the second one is $1, the third one is $2, and so on. And that's what I'm doing here. We don't need the type definition for the in parameters because we said string already defined this for us. Nice. We don't need the parameter definition itself because it can be shortened with those shorthand characters. So as soon as you write $, the Swift compiler goes back, has a look at the function, how it's really defined on string itself, makes a clue out of it, comes back and knows, okay, you didn't write it, but I know what you mean with the $0 and $1. And as we said before, I just have one statement. I don't need the return value. So nice. But we can do it shorter. No shit, Sherlock. You can just write it like this. And yeah. And why can you do this? Because the string type is so nice to you and has overwritten the lesser and greater parameter for you, so that this comparison of two values is done for you. And as soon as just this operator is used, the rest of the magic is done for you. So it's really a long decision tree and a lot of things the language does for you to make this really happen. If you should write code like this or code like this or code like this, it's completely your own flavor, because shortening your code is always making the readability of your code. Yeah, we all know this, but it's basically possible. And I think this is kind of awesome and very explanatory, because you sort it this way, everybody knows it's ascending, so that's a good thing. But it's astonishing what the language really does for you in this place. Just for convenience, you know this, in Objective-C, I'm out. I always have to look up fucking blocksyntax.com. But in Swift, it's gotten really easy. But in any case, you don't know the syntax for closures in Swift. That's the URL for you. And we always need helpers on place. So it's just here that you can look it up. Good. Now we have a little bit of sugar on the top. And it starts with an question mark and follows an exclamation mark. And you know what's coming? It's the optionals. And that was, for me, the hardest part in Swift, because I wasn't used to a structural, logical thing like this. I know it's not new, because a lot of languages already have it in place, call it optionals too, or maybes. No? But as soon as you have a look under the hood, what an optional in Swift really is, I was completely amazed, because it's so simple. It's just some enum which holds nothing or something, and then it's wrapped for you. So that's all. That's the optional. And we are using it basically with those little short forms, but you could use optionals this way too. You could really write optional, wrap your type, and then attach your value in there. So that's kind of this safe container, which is offered you with this wrapped type. And yeah, when I define an optional string, then I attach a value to it, define another variable with the same value in there, and then be a good citizen, because check for nil, yeah, that's what we learned from Objective-C, and then print those two. What is happening? This was really not logical for me, because where is this optional string coming from? Yeah, and that's exactly this. In an optional, you have the safe container, this wrapping type, which looks like this when you print it, because you have to unwrap it explicitly, because otherwise such a safe container wouldn't make very much sense. So I guess nobody of you ever used optionals with this syntax, so this is more what you're doing. So there's a short form where you say, okay, I'm not sure, this might be a string, might be not, and I'm attaching a value to it. Then I try to print it. Then I try to print it with the exclamation mark. And yeah, then I try this thing Apple says, always conditionally unwrap. So ask before if something is in there and then use it. So all those three things might go well. But what happens here, again, because this is still wrapped, we get the optional and then the value in there. When we use an exclamation mark, so that's kind of a thing a lot of people which were new to Swift did, always use the exclamation mark because then it works. So somebody told me, as soon as you use exclamation marks, your code might be kind of dirty. Yeah? And when you reflect a bit how you coded Swift in your first phases, I would say, there are surely a lot of exclamation marks in there. So try to really avoid those, because you can use Swift in a very, very secure other way. And that's basically it. Conditionally unwrapping, you first ask if something is in there, and if something is really in there, then you could really use it. So, and then I think it was with Swift 3, correct me if I'm wrong, the guard statement came to place. And now you can do the negative check kind of. With if let, you're doing the positive check. You're asking for something. Is there something in there? Okay, then I use it. And in this case, this is kind of your security parachute. You ask if something is in there, and if not, then something happens. So, but my problem was to really understand why I have the guard let my name, and this one gets the value from this variable and can be used in a complete different code block. Because isn't this the code block here from this guard statement? No, it isn't. So this block statement here is really just the else case. And this here, so the my name variable, is really defined in the global context here. That's why you can use it right away. So you don't have this exactly if block, else block. You're just running into the else block and can use everything you define with the guard let here, which really got the value down there. So that's kind of something which is not completely sequential logic when you have your first thought about it. But after really having a deep look, it kind of gets clear that you can use this variable here safely as the quite the same way as if you say if let my name is name. So this is kind of the same. Good. Okay, and before we always use the question mark here on the optionals, we can use the exclamation mark too. And with the exclamation mark there, you are telling, so it's your responsibility, you are telling the compiler, I make sure that something is in there. And then you don't have to conditionally unwrap something. Yeah, you should, yeah, but you don't have to. You don't have to say you need the exclamation mark here. There is no optional printed out for you. So it's really just You tell the compiler, I take the responsibility. I tell you there is something in there. No worries. And I swear to you, every time I use this, it crashed somewhere. So I don't know why this is really offered, because the idea of an optional is to tell the compiler, please have a look. I don't know for sure if there would be a value attached to this variable, but this is the way you can go to. In some cases, you might need them. Okay, and in any case, the whole type system is kind of, I don't know, Latin to you. You don't use Swift that much. It's kind of just interesting to hear about it. I thought some fun facts at the end of the talk would be kind of nice. So everybody of us Swift developers knows those Taylor Swift jokes, yeah? And I found a really good one. So Apple to Taylor Swift into an open source language for Linux too. So this, yeah, I know it's very low level, yeah, but they tried. And another one I really enjoyed is there you need to have insider knowledge. I really had to Google, because I'm not a Taylor Swift follower, more than a blank space that Swift design has in common with Taylor Swift, and blank space is a single Taylor Swift has released. Whoa. And those are the actual facts, which the programming language and Taylor Swift really have in common. In any case, you really want to read the full article. I can give you the URL, but to keep you safe, I've hidden it. But that's actually, yeah, no Swift talk without Taylor Swift. That's the law. Good. So basically, this is the end. We covered really all of it. We talked about compound types. We talked about name types. We talked about function types, which are constructed out of tuples. We talked about closures, which make use of function types for the signatures. We talked about optionals. We talked about type aliases. Basically all of it. So you are now officially Swift type system experts. Congratulations. And that's basically all. Thank you.
All right. Questions, as usual, you have to shout it and we will repeat them. Just moving, and in the meantime, otherwise I have a question definitely, always. But you're first.
Thanks for your talk. You mentioned that you use tuples in functions.
Mm-hmm.
Define functions.
Mm-hmm.
When you define a function, you can provide two labels for the underscore thing.
Mm-hmm.
If I try to define a tuple with two labels, the compiler says no.
Because this is a speciality which is offered to you as soon as you use the func.
Yeah,
keyword.
we need to repeat the question because of
sorry.
the video. So you repeat the question.
Why can I use an inner and the outer parameter name with functions but not with tuples? So that's the answer. It's really just with functions. So that's kind of Swift being nice to you. You can say, hey, I don't want you to bother the user by really typing in a parameter, but sometimes that's very nice because it extends the name of your function. But those two parameters which you can put in place are really just possible as soon as you use the func keyword in front of it. That's it.
Do you keep that last slide for after, or do you want to play that last slide? Because I think it looks good, so that's why.
That would be my last sentence. If you want to have the talk slide deck, just copy the QR code, or if you are old school, just go to speakerdeck.com, look for code printers, and there you find it too. When you think QR codes are
Makes me think we should have used a QR code for
you should have
for that
maybe.
link at the beginning of the keynote, whatever.
Next time.
Yeah, if you have another question, just be ready. Note for all the other speakers after that talk, think about repeating the questions, because I am very bad at repeating the question. I discovered myself, so this is your job. It's a funny job, especially if the question is like 2 minutes long. And yeah, if you ask a question, try to keep it short because of this. Somebody else.
I know it was the most boring one. Oh,
Yep.
cool. Yeah.
Shout it, because you're at the back.
We'll debate after.
Oh.
Before there was a change about how they handling single tuple versus tuple more broadly in closure and function. I don't know if you heard about it, like basically now, like if you have a closure that takes a tuple and it's a generic, you can't call it with void. You have to use just the void parentheses.
We've had this before. Everything concerning generics we take offline. Thanks.
All right, so we didn't repeat the question, but whatever. It's too long.
It's very complicated.
Yeah. All right, so we already are actually running a little bit late, so I will release you, but not before you give an amazing round of applause for Manu.
Thank you.
All right. So see you in about 10 minutes.